Yeah. All right, thank you. Yeah, so last time I spoke here at the Simons Institute, I talked about quantum algorithms for chemistry within error correction. So this time we're going to the far extreme of the quantum chemistry and quantum computers field and actually talking about an experiment on a NISQ device. So I'm going to start with just some overall context about where we are today with quantum computing. I think most of you are probably on the same page with this, but we're in the NISQ era. This means we have noise in our circuits. Maybe we can do circuits on about 50 qubits or something, but we're severely limited in the size of circuits we can perform. Last year, our team at Google demonstrated this quantum supremacy milestone, which means that there's at least some contrived computational task that we can solve on our device, which would be in practice and feasible to perform on a classical supercomputer. But this doesn't mean that we're about to start solving useful applications on our device necessarily. So the ultimate goal of our group is to build an error-corrected quantum computer. And certainly many of the quantum algorithms that are discussed at this conference and sort of the vision of quantum computing that we have in our dreams would require this. Of course, quantum error correction has very large resource overheads, and we can sort of think of this in terms of the number of qubits. So if we're thinking about implementing the surface code with error rates similar to what we've demonstrated in experiment, then up to about 50 qubits, you could classically simulate the circuit. The quantum supremacy experiment shows we're sort of just beyond that threshold. But to start doing useful things, as far as we know within the surface code on a fault-tolerant quantum computer, you're probably going to need hundreds of thousands of physical qubits at these error rates. So we have a roadmap to get there. We're very serious about getting there. But it's going to take a while. And we're going to have devices that are smaller than that in the meantime. It's sort of worthwhile to ask, are these devices in the meantime going to be able to do anything useful? And that's sort of the activity of seeing what we can do with NISQ devices. So I'm going to quickly review the quantum chemistry problem because this talk is about doing quantum chemistry. So the goal is to solve for the energy of a molecule. Molecules have protons and electrons. They're interacting with the Coulomb operator. They have kinetic energy. And you've seen this curve now a couple times. There's one drawn behind me, but it's the binding curve for a molecule. There's 1 degree of freedom here. So we're solving for the energy of the electronic wave function. And energy surfaces like this, they allow us to understand chemical reactions, but we need fairly high precision in order to do that, in order to predict chemical reaction rates. So, Garnet gave a talk earlier about sort of where classical methods for quantum chemistry are, and he's certainly correct that you can do sort of more than you might expect with classical methods. But especially for systems with strong correlation, there are plenty of examples where achieving the level of accuracy we need to predict rates and mechanisms is quite challenging on classical devices. And so these are sort of the systems that we think about solving on quantum computers. So finally, I should say that to represent the wave function on a quantum computer, we have to confine it to some basis. So usually we're thinking of a basis of orbitals, like molecular orbitals shown here. And we're usually working in second quantization. So for instance, if we have 4 orbitals, which are places that electrons could be, and we'll have 4 qubits, and each qubit represents one of those orbitals. It's 1 if there's an electron there, and it's 0 if it isn't. So everyone sort of loves applying these variational quantum algorithms to chemistry. And this is actually a fairly small sample of the experiments that have been published that are actually experiments computing binding curves for molecules on real processors. So this is probably maybe a fourth of what's been published so far. They've done it on ion traps, on photonic devices, on superconducting qubits. But it's worth noting that the largest of these experiments that have been performed are on only up to 6 qubits. So you can be kind of confused about what molecules people are solving. Sometimes people say they're solving a water molecule or a benzene molecule, and really they're just simulating 3 electrons on it or something. But to first order, the number of qubits being used is a pretty good measure of how big the experiment is. And the fact that we've only seen these experiments up to 6 qubits, that's an indication that these experiments are quite challenging. And we'll talk a bit more about those challenges. But it should sort of give us pause that we've only done these experiments up to 6 qubits. So what is the point really of doing these application experiments on NISQ devices at all? So there's a couple cynical reasons you could throw out there. So one of them is that it's definitely easier to publish these experiments in Nature than most of our theory work. That's a very bad reason, of course. So another reason, and I think this is actually kind of a serious reason, is that it's often, I think, a good thing to sort of force algorithmists like us who work on algorithms to actually feel the pain of a real experiment, which can be pretty substantial. You learn that there's a lot more that you need to do to sort of get performance out of the device than you would think. If you're not using a qubit for a while, is the best thing just to apply identity there? Probably not. You should probably be applying spin echoes like X gates. How often should you do that? There's lots of little tricks like this which are good to learn. But I think another reason is that, to some extent we can sort of disagree over, whether we should be focusing on benchmarking our devices with randomized benchmarking or cross-entropy benchmarking or quantum volume or something. But these application experiments that, a lot of people are trying to do, I think it provides something of sort of a system-level benchmark. What sort of quantum chemistry experiments can you do on an ion trap or a superconducting qubit system? I think it's telling that at this point we've done 4 times larger quantum chemistry simulations on superconducting qubits than on ion traps, and not for lack of people trying on ion traps. So to some extent, I think that these experiments help us sort of compare where our device is relative to competitors. But probably more importantly, if we ever think that NIST devices might be useful for solving actual applications like in chemistry, maybe it's apparent that the particular methods that we're using today aren't quite there. We need to develop better error mitigation techniques or something like this. But it would be useful to know, exactly how far away are we from doing something that's really interesting. Are we at 5 qubits or 10 qubits or 25 qubits? And so it's sort of a way of measuring our progress towards improving these methods and improving the devices. I think perhaps the most important reason, though, is simply to sort of study the effects of error mitigation techniques, because this is something which is very difficult to do in simulation. You often don't actually know, good models for the noise affecting your devices, and it's kind of apparent that for NISQ algorithms, error mitigation's essential. So the best way to tell how those things are actually working is to just try them out. All right, so what experiment did we actually perform? It's maybe not the experiment that a lot of people were expecting the first chemistry experiment on this device to be, but it's one I'll spend a while sort of explaining the justification for. It is a variational algorithm, as I'm sure no one is too surprised by that. But the ansatz that we use in the variational algorithm is actually an ansatz that corresponds to changing the single particle basis that we're using to represent the wave function. So if we started with orbitals like the ones that I've drawn here, the unitary that we're going to apply, it changes the basis such that we're now on a new basis which can be written as an orthogonal linear combination of this old basis. And the unitary that this corresponds to is a very simple form. It's not an obvious form that you would have this correspondence, but it's due to something called the Thulis theorem, essentially. So basically, these arbitrary basis rotations can be expressed as a unitary that's generated by evolution under a free fermion Hamiltonian. And so this is what this basis rotation would look like, where these kappa values have the relation I've written here to the coefficients of the actual basis change. So when you use this ansatz in a variational algorithm and then you optimize the parameters, you're actually applying what chemists would refer to as the Hartree-Fock procedure, which is a mean field algorithm for approximating the ground state energy. And this is actually, so one way to think about this is actually usually this algorithm is run as a way of computing these orbitals. So if we think about what we're doing here, we're starting in some product state essentially, and we're applying this unitary, which I've described here. We can actually think of this just as a basis rotation on the Hamiltonian, and we're essentially solving for the parameters of that basis rotation, which allows sort of a product state to express the lowest possible energy. In other words, we're solving for the lowest energy basis for the system. And of course, this procedure is completely classically tractable. Usually it's the starting point for these quantum algorithms for chemistry. So why are we doing that on a quantum computer? And to be clear, we're not getting a speed up over what a classical algorithm would do here either. So there's a couple reasons. I'll get into this one a bit more. But first, these basis rotations are a fairly ubiquitous primitive in quantum simulation. I'll argue that they're sort of essential for many of the best algorithms we have for simulating chemistry or Hubbard models or things like this on a quantum computer. So it's a primitive we're going to want to apply anyways, and learning how to do it well is by itself sort of valuable. And also, it's a primitive for which we have a compilation which is known to be optimal, which I'll discuss too, which is kind of nice. And because of these things, I think it makes sort of a great benchmark. So to the extent that we're interested in, sort of comparing how different platforms are doing for quantum chemistry, I think this, achieves that goal. The other thing is that while it's a state that has some structure which allows us to solve for it classically, from the perspective of the quantum bits, it's a very entangled state. If I just sort of gave you this state, you would have a difficult time telling that it's not some very complicated state. The structure in it's sort of hidden. And this is actually very much a feature of the experiment because I won't have too much time to get into this, but in the paper that we'll have out fairly soon, we sort of discussed that this structure gives us a lot of insight into how errors are affecting the system. So for instance, we can efficiently compute the fidelity of the state that we're preparing without doing tomography. Or we can exactly compute what the systematic errors were in the circuits that we applied and things like this. And also, as I'll mention briefly, the structure of this particular choice somewhat simplifies the implementation that we face. Okay, so why am I so obsessed with basis rotations? And I think this is such an important thing to practice doing. So, when you write down the quantum chemistry Hamiltonian in the normal molecular orbital basis, you get this very complicated object which has n to the 4 terms in it. And that complicates, the number of measurements you have to make in BQE. That complicates the number of gates it would be in a Trotter step. It complicates a lot of things. So, one comment is that if you use a simpler basis, for instance, these sinc functions or something which are related to plane waves, you can get a much simpler form of the Hamiltonian that has only n squared terms in it. And so, Hamiltonian like this, which is, expressed using this basis, you can perform measurements much easier. The Trotter steps are much smaller. There are some downsides of a basis like this, namely it's less compact. So you will often need more qubits to represent the system. But often it's still a good trade-off. And if you want to use a basis like this, that's great. The Hamiltonian is simpler. But the state you start in, which is a product state, is now going to be a product state in this basis, which has probably very little overlap with the ground state. You'd rather start in a state that's a product state in this basis. And so the first thing you have to do is you have to apply a basis rotation in order to rotate yourself into the correct basis if you're going to perform any simulation in a simple basis like this. Also, to actually perform something like the Trotter step here, probably one of the more sensible strategies, in fact the strategy which as far as we can tell has the least Trotter error for simulating this Hamiltonian, consists of first simulating this potential term which is diagonal, and then applying a basis rotation to diagonalize the one-body operator, and then applying that where it's diagonal, and then switching back. So the Trotter step would also involve basis rotations. Finally, and Brigitte touched on this briefly in the end of her talk, if you don't want to make this trade-off where you lose compactness in the representation of the Hamiltonian, you don't want to use plane waves, that's fine. You can take this Hamiltonian written in this basis and you can express it this way. It's essentially a factorization of the Hamiltonian which expresses the hard part, the Coulomb operator, as a sum of n different diagonal operators, each in a rotated single particle basis. And so if you write the Hamiltonian like this, it's apparent that you can do Trotter steps in only n depth by first applying the basis rotation, then applying this diagonal part, and then applying the basis rotation again, and just sort of repeating that for each of these different bases, of which there are n. And that just comes from sort of some structure in the Coulomb operator that factorization ends up being low rank. The final thing I'll say about this, and this is specifically what Brigitte was talking about, is that when you're interested in measuring the energy of the Hamiltonian, which is something you want to do in a broad number of contexts. So for instance, this is required in Garnett's kite algorithm, even though that's not a variational algorithm. One of the most effective ways to do that is to first apply this basis rotation and then sample these terms which are diagonal, and do that for each of the different bases. And the reason why that's a good idea is because it reduces the variance of these operators. It means there's many fewer circuits that you need to sample in order to estimate the energy. And all of your energy estimates end up being diagonal, which has the advantage of commuting with the particle number operator. And that means that you can simultaneously post-select on states that have the correct particle number. So that can also be an effective form of error mitigation. So anyways, all of these things require basis rotations. These show up everywhere. They show up for the Hubbard model too. So it's in general a pretty important primitive. All right, so how do we actually realize these basis rotations on a quantum computer? So we had a PRL about this a couple years back. But again, this is the operator we want to apply, this sort of arbitrary free fermion evolution. Now you might think, oh, we should just trotterize this, but it turns out that because these one-body operators have a closed Lie algebra, there's sort of a nice way of applying it that's exact and doesn't require any trotterization. And in particular, if we are going to apply this to a state that's at half filling, which is what we're going to be doing in our experiment, we end up with a circuit that has a structure that looks just like this. So it's something which you can apply on even a linear array of qubits. So you need just minimal connectivity to do it. And each of these 2-qubit operations here corresponds to a so-called Givens rotation. So it's an operation that looks something like this. And the idea is that you sort of figure out what these thetas are by this procedure where you apply a sequence of rotations that look like this to the kappa matrix in order to diagonalize it, which is sort of just a complicated way of saying the value of theta here is some function of the kappa in this expression, which you can evaluate classically. Of course, this is not a native 2-qubit operation on our device, but we can realize it with some gates that are, in particular, 2 repetitions of the square root I swap gate. That's a gate that we have on our hardware. And some single qubit Z rotations will implement this operation. Okay, so the last thing before I really get into some results from the experiment here is I also want to explain that this choice of variational ansatz, it also somewhat simplifies the implementation of the variational algorithm. And it does that in a couple different ways. One of the ways corresponds to needing to make fewer measurements. So usually we would have to estimate the energy of the Hamiltonian by sampling all of the terms in this expression here. And of course, these 2-body terms, of which there are n to the 4, those tend to be the most problematic. And I'll introduce a little bit of notation here where we think about all of these PQ expectation values as a matrix. So this, we just collect these expectation values into an n by n matrix. So that would be called the 1-particle reduced density matrix, or 1-RDM. And all of these expectation values organized into a matrix, they'd be called the 2-particle reduced density matrix, or 2-RDM. So it turns out that because this Hartree-Fock state that we're producing is a mean field state, the 2-RDM can be completely, you can obtain it through accumulant construction from the 1-RDM using the expression that I've written down here. So in other words, you actually only need to measure the 1-RDM for this experiment in order to completely determine the energy. And that means that drastically simplifies the number of measurements that we have to make for the experiment. I should also mention that these RDMs that we measure, they have certain known structure. And some of these are sort of structure that will apply even for a completely arbitrary quantum chemistry ansatz. For instance, the trace of the 1-RDM needs to equal the number of electrons in the system, which is just a way of saying that the wave function needs to have support entirely on computational basis states that have a number of 1s that's equal to the number of electrons, which is kind of obvious from the encoding. But there are some other properties that apply in this context too. For instance, the 1-RDM needs to be positive semi-definite. That's actually always true. But it also needs to be idempotent. And this allows for a form of error mitigation where we can actually purify the 1-RDMs that we obtain. And so what I mean by this is we obtain some estimate of the 1-RDM from the quantum computer, but say there's some noise in it, maybe we didn't make enough measurements or something like this. So it's possible to project that 1-RDM to the nearest 1-RDM, which is consistent with having come from a pure state. And there's an efficient procedure for doing that. And so that's a form of error mitigation that we're able to use in this experiment. Now, the particular form that we use, which is called McWeeny purification, that applies only to wave ansatz of the form that we're studying here. However, more generally, there are known conditions on the 2-RDMs that would apply in a totally general context for variational algorithms for chemistry, which are conditions which must hold only for pure 2-RDMs. And so, in principle, there are versions of this that would apply more generally as well. But we don't need them here.
Why doing McWeeny purification instead of just doing a singularity decomposition threshold?
You could do that too. Ultimately, it's just a way of restoring idempotency, so it's the same result. Okay, so I should probably say something about the hardware platform right before getting into the data here. So this is a picture of our Sycamore processor. It has 54 planar transmon qubits. You can't really see the qubits because we make the qubits on one chip and we make the wiring on another, and we kind of solder them together, and the thing's already flipped over, so you can't see the qubits here. Here's a picture of our refrigerator with our CEO standing in front for scale. So the thing that we're sort of most proud about this device is the error rates. So Jared mentioned this yesterday, but this is a schematic of what the chip looks like. The X's are the qubits, and the boxes are the couplers between the qubits. And here we're showing the error rate distribution across the chip, but we have less than 1% error in the 1 and 2 qubit gates, even when they're implemented in parallel across the entire chip on average. The readout error is hovering around 4%, which is something that we can certainly improve, and we're working to improve it. But especially when the goal is to measure expectation values, as we're doing here, readout error is not so much of a problem, because usually what's happening is you have T1 decay during readout. So that means that some percent of the time when you measure a 0, it was really a 1. But it's very easy just to do a calibration to tell. If I know that 4% of the time I measured a 0, it was really a 1, you can just factor that into your estimate of the expectation value, and it's not such a big deal. We should say that most of the data for this experiment was collected through a cloud interface to the device, which our team is fish fooding. That means it's before dog food. We're sort of testing it out before we release this to the public. But we use Circ to control the quantum computer, and we used Open Fermion for all of the chemistry-related parts of the calculation. All right, so with that, how well does the machine actually do? And I should probably first say, what did we actually do? So we did a couple things. One of them is we made more of these curves, hooray. But this time, it's not just for molecular hydrogen with 2 hydrogens, but we actually looked at a series of different hydrogen chains. And we did H6, H8, H10, H12. And so, of course, H12, that's not a real molecule, but this is a very simple benchmark. It's a nice benchmark. As you stretch it, you kind of scale the system between regimes of strong and weak correlation. And we're sort of not obscuring what we're doing in some weird way here and doing 3 electrons and calling it benzene or something. It's just what you see is what you get. So we thought this was a good benchmark, and I'll show you those results. The other thing is, we're all a little bit tired of doing these diatomics, so we wanted to do some example of a system that really felt like you were doing chemistry. And in particular, what I meant by that is you're actually trying to resolve the correct chemical reaction mechanism for some system. So we focused on the diazine isomerization. So diazine it's basically hydrogen peroxide, but with nitrogens instead of the oxygens. And it can be in a configuration like this or like that. And it's rigid because it has a double bond. It can't just spin over easily. But it can isomerize between the two, and it can do that by going like this, where this guy moves out of the plane, or it can go like that, where it moves in the plane. And there are 2 different mechanisms for that. And you have to compute the energy surfaces, and you have to see which one has the lower energy surface in order to resolve the reaction mechanism. So we wanted to see if we could do this, at least within the model chemistry that we're studying, which is Hartree-Fock. Okay, so first I'll talk about the hydrogen chain benchmarks. Again, for something like H6, we have a circuit that would look like this. I should say that often you think H6 is 12 electrons. For us, it's 12 qubits. It's only 6 qubits for us. And that's because of the fact that we're focusing on Hartree-Fock. It allows us to just focus on just all of the up spin electrons or something like this, because it's a singlet. So anyways, this is the curve that we obtained for H6. Both of this data is shown after variational optimization. The green dots are before we apply air mitigation, and the blue dots are afterwards. The air mitigation, again, corresponds to post-selection on particle number in this McWeeny purification procedure. And so I should say this is 6 qubits. This is already on par with the biggest, the biggest previous chemistry experiments have been 6 qubits. This is already about the scale, perhaps bigger than the biggest ones previously. But we also did H8 and H10 and H12. So this is now, well over, I think it's something like 5 times the number of gates as the largest prior experiments and double the number of qubits. And, at least qualitatively, we have pretty good accuracy here. It's not perfect chemical accuracy, but none of the results at 6 qubits were either. This certainly highlights some of the challenges of doing chemistry in the NISQ era. Obtaining this very high level precision is quite challenging. But overall, we're getting good qualitative agreement, and that's that's something I think is quite positive.
Oh, I was just wondering, is the solid curve, is that the exact Hartree-Fock?
It's Hartree-Fock, yeah. So we're doing this relative to the model chemistry. Indeed, if you were comparing this to, I think this is kind of the proper comparison too, because sometimes people will put the FCI curve there, but of course that's just the FCI curve within the basis. What is FCI? FCI would be the exact diagonalization within the basis. But that's still within a model chemistry. It's within a basis.
But in this example of the reaction rate, does the Hartree-Fock get the right answer?
Well, we'll get to that in a second. So this is just the binding curve. There's no reaction rate here. But we'll talk about that with diazine in a moment.
Sorry, you said you had 6 qubits and how many gates?
So the number of gates is n squared over 2. Sorry, that's the number of 2 qubit gates, and then there's 4 gates per, so it's 2n squared is essentially the number of gates. But I've written out the number of gates here too. So it's 18 square root I swaps and 27 RZs. Maybe that's an easier way of doing it. This one's 72 square root I swaps and 108 RZs.
What's the difference between the green and the blue?
The green one is with is what we get before error mitigation, so before this post-selection on particle number and the purification.
I can't see from here, but there aren't error bars on there, right?
There are error bars on here. There are. They're very small. Yeah, we did enough measurements. Yeah, maybe that screen's higher resolution.
Are you tuning the RZs and the I swaps? Like where?
Nope. No. So it's actually, that's a good question. So I'm not going to click all the way back to that slide, but okay. So the number of parameters is if you look in here, it's sort of like the number of parameters that appear in here, and there's a couple symmetries that reduce it even further. But the RZs are sort of a function of what these kappas are, and there's actually fewer variational parameters than there are RZs.
Can you say how many variational parameters there are?
Well, I don't recall exactly, but 27 RZs. I think it's probably on the order of, I think it's a little bit less than half, probably. So there's probably about 50 variational parameters here. Maybe like 12 here, roughly.
Is there variation from run to run?
So that's a good question. Yes, there can be, but the results that we're showing here, like the procedure is not to just sort of run it until you get the results that you like. Usually when we have variation between the runs, we try to figure out why it is, and often, we figure out something like, oh, the AC was turning on and off in the room during this run, or that actually was something we noticed.
When I was showing error bars on everything, that's all from the variation from run to run. Measurements. I was just curious, if you were to put a scale on that variation, how big is
that? So that should be. It's worth mentioning that many of these points, they consist of hundreds of thousands of measurements, each of these points, which are averaged over, which are not even, those are collected over a period of time that's long enough to see effects from things like 1/f noise. So I don't think that, in general, you'll see much fluctuation from that.
Sorry, can you say a little more about this? So is the assumption that you're getting a signal and the rest of it is background noise, so you can just average it out, or what's the model here in terms of noise?
Okay, so we're applying our circuit, and then we're sort of sampling these things that correspond to the energy, and we're performing the variational optimization, which I'll show the data for here. So there's probably some fluctuation in the way that the variational optimization performs. In some cases, it may take more iterations than in others, but ultimately, I think that we will converge to the same point.
Is the retraction back to the manifold done classically?
Yes.
Are you bootstrapping through the calculation starting from one side? Like, are you using parameters from a previous execution as a starting point, or are you using a consistent starting point throughout, or random?
We're starting in the atomic orbital basis.
So those are classically computed initial parameters.
They're not really computed. They're sort of just a function of the basis set that you use. So it's like whenever you're using hydrogen, you know that you're taking these, you have Gaussian centered on hydrogen that look like this. And then there's a procedure that's like, Graham orthogonalization to make sure that the orbitals are orthogonal, and that's what we use. But they're not optimized in any way for the molecule. That's what the Hartree-Fock procedure is doing. Yeah.
Just one more time. The black curve then is the optimization of the...
This black curve?
No, one on the left.
This is the Hartree-Fock energy.
But that means, given the set of basis states you have,
Yes.
it's in exactly the same dimension as...
Yes. Yeah, although that solution is actually only dependent on the number of primitive basis functions, of which we're using many. So as you add like number of qubits, the black curve doesn't move. It will always be the same because Hartree-Fock only...
In the real world, how far down is the curve, in the experiment or something?
If you used like the continuum basis and you did FCI, I don't know. It does look differently though. But I mean, that's not accessible to our experiment, so we're not comparing to it. All right. So here I'm showing some of the traces from the variational optimization. So I want to point out that this is on a log scale on the y-axis. So, okay. So we're getting convergence here across 1.5 decades, which I think kind of speaks to this question that I was being asked about a moment ago regarding what's the convergence of the procedure, and sort of strengthens some of our conviction that we're actually converging to these points. I mean, you can't go lower than this energy, and we do tend to get to this point. So this is also another reason why I think that it's reasonable to suspect that the experiments run tomorrow are going to look the same.
In the stretched configuration, which is the purple, the error seems to be really small, even without any optimization. Am I missing something?
Yeah. I mean, so the reason for that would be because we're starting in an atomic orbital basis. And so the further away you are, the more treating the orbitals like they're on individual atoms and they're not bonding, the better that approximation is, I would think.
Are you doing the restricted Hartree-Fock?
Yeah.
Because that still doesn't look like a product state in the atomic. That's still very far from the product state.
It's still a molecular orbit.
Yeah.
Where the Hartree-Fock gets wrong.
So, yeah, I mean, this is still well outside chemical accuracy, though. Yeah. Anyways, yeah, I think we're just starting in the atomic orbital basis, so I'm not, so in any event, I also want to point out that the optimization procedure we use, it's sort of a Newton-Raphson procedure that we cooked up, but it's also using gradient information, which we're able to obtain from the 1RDM, which is sort of a nice property, again, of the Hartree-Fock ansatz that we're looking at. So I also, here we've broken out, this is just for H6, by the way, here we've broken out some of the different contributions to the air. So I believe that this is the curve before we've applied the post-selection. This is the curve after we've applied the purification. And then this is the curve that comes after the variational optimization. And so to some extent, very loosely, you could think about these three procedures as correcting different types of air. This one correcting essentially T1 air because it's just restoring the particle number to what it should be. This one correcting T2 air. And this one adjusting for coherent errors or control errors. Okay, so finally, here is our diazine curve, which frankly we are still working on, and I expect it will improve some before we actually publish this paper. But before, David was asking about what the correspondence is between the actual diazine curve in FCI and what it is in Hartree-Fock. And in Hartree-Fock, it doesn't look great. It has some cusp here that's as a result of the calculation being Hartree-Fock. But again, the point here was just to sort of study convergence to the model chemistry. So, how well are we doing here? We're doing okay. We're actually able to correctly resolve what the transition state is within the model chemistry. But indeed, it would be good to see these values improve. So anyways, that was all the data I planned to show. So what did we actually do? What did we learn in this experiment? Well, the first comment is we realized what is by far the largest NISC quantum chemistry experiment. It's larger than, or it's twice the size of the largest prior ones. But quite frankly, as you all have seen, I think that there are some real challenges here. I think it's very unlikely that we're going to be able to have similar results that would scale past about 20 qubits unless the error rates improved very substantially, and I don't think that they will. So to some extent, I think that just sort of refinements of the paradigm methods that we're already using may not be enough. I think that we may need some fairly big ideas to go beyond this, or a couple sort of big breakthroughs in the way we're thinking about things like error mitigation. But that's okay. I mean, at least we sort of know where we stand with things today. So again, the ansatz that we looked at, it corresponded to arbitrary free fermion evolution, which when optimized gives you the Hartree-Fock solution, which is, in some sense, if you're just coming from the quantum chemistry world, the first thing you might want to ask is how well does the thing do on Hartree-Fock? And again, this is a primitive that comes up all over quantum algorithms for chemistry. So it's one that, independently of this experiment, we think that we'd want to be able to do quite well. We did see the algorithm performance improve quite a lot due to error mitigation procedures, such as post-selection, this purification on the RDM, and variational feedback. But like I say, still, I think we have a long ways to go before we're doing anything classically intractable in the NISC regime. Or perhaps we're just going to need to wait for error correction, which is a possibility as well. So with that, I want to thank, first of all, the whole Google team. This is a new chip that was we accessed largely through a cloud interface, and that took an enormous team effort to support. But I also especially want to thank Nick Rubin, whose picture is up there on the right. Nick actually designed and led much of this experiment. He might have the answer about why that atomic orbital starting point looked so good. Also Charles Neal on the hardware team, who helped sort of run the experiment and get to the bottom of some of these issues, like is the AC on or not. And then Zhang Jiang and Vadim Smeliansky were also quite helpful for sort of helping with techniques for calibrating the device and improving control and this sort of thing. So, thanks.
And then panel discussion. So maybe one or two quick questions. Yeah.
So if you want to move past Hartree-Fock, what do you think is going to be the major obstacle?
So frankly, the number of measurements required, I think actually adding correlation to the ansatz is going to be extremely straightforward. In fact, we're already sort of working on it. Basically, in that circuit that I've shown that's generated just by XX and YY terms, if you add a generator that has some ZZ component, which would require one more entangling operation and two more single qubit operations in each of those 2 qubit gates we're realizing. So it would increase the gates by 50%, but have a circuit look the same structure. Then you have something which would be classically intractable to, if scaled up. It's not Hartree-Fock. It's something that has a lot of correlation in it, and we have some ideas about how to get good parameters for that.
Yeah. Have you looked at the generalized Hartree-Fock based on non-particle number conserving Gaussian?
Sure. Yeah. So preparing fermionic Gaussian states. Yeah. So that's something else that we could have done. Actually, we're working on another experiment that's about the Hubbard model, where we do prepare a BCS state, which is an example of this. We could have done that. So for chemistry, it's kind of a nuanced thing because you know that the correct ground state is supposed to have certain symmetries, but in practice you can get lower energies often by breaking those symmetries. That's especially true because we're in a smaller basis. This is kind of like a basis artifact thing. So we could have done that, and that probably would have been interesting. The fact that you break those symmetries, though, makes some of the error mitigation procedures we're using less effective because you can no longer post-select on spin and particle number.
All right, we're going to have more opportunity for questions in the panel, so let's thank our speaker again.